Okie dokie. In the last video, I looked at prepping for the calculation or for the proof, I suppose you'd like to say, that the function I showed you is indeed a probability density function. So let's continue on. So we set this up by transforming x to this z scale here, right? By subtracting the mean mu from z and then sigma. So that got us to where we are here, and I showed you what I did to get to this point. So now we're left with, let's call this function I, right? And we can't solve this with conventional means, so there's a little trick. If you start studying about the proof, not just from this video, but from a bunch of different videos, how to prove this function, what you'll see is that the trick was to square it, so just to raise it to the second power, and then all of a sudden you get two of them. Like, hey, one isn't enough, so let's get two of these functions. Maybe we'll do better. Let's try it. Well, it's not, one thing I've learned about mathematics is that it's full of these little tricks, and thanks for the people who discovered these tricks. Make life a lot easier for all of us. So let's square I here. So this is the function we're trying to prove is a probability density function. We just square it, right? So I get two of them, right? So I get so instead of 1 over square root of 2 pi, now I have 1 over 2 pi, and this is just a constant, so I'm not really as concerned with it yet. We'll use it later to help us achieve our goals. And then we have two of these functions here, e raised to the, e is Euler's number, in case you're not familiar, but I'm sure you are by now, e raised to minus z squared over 2 dz, and then again, the integral from minus infinity to infinity of e to the negative z squared over 2. So we got two of them. Yay, I'm so happy. I'm smiling. All right. I can actually smile without a mask. This is cool. Yeah. So let's just change one of these variables to y. It doesn't really matter if it's z or y. It's just two different variable labels. We're not doing anything else here. We're just changing the label. So now we have e raised to minus z squared over 2 dz, and then we have the same with minus e raised to minus y squared over 2 dy. We still have the 1 over 2 pi out here. So we just rearrange just to make it a little easier. Since this is a multiplication of two of these exponents, two of these Euler's numbers, pardon me, raised to these two different ratios, I can just go ahead and add the two exponents together, right? So I get minus 1, and I take out the minus 1/2, because both of these have minus 1/2 here. So I take out minus 1/2, and it becomes z squared plus y squared, and then dz dy. Those are this is the rest of my integral here. Now this is starting to look a lot like, you can see the Pythagorean theorem. So clever people will notice that, right? So you'll say, well, why don't we call this something else, like r squared equals z squared plus y squared. So we'd like to simplify this. So we'd like to substitute z squared plus y squared with a single variable, let it be r squared here. And one way we can do this is to switch from these Cartesian coordinates, right, this x and z here, to polar coordinates. We have this circle here, polar coordinates, and the r here becomes the radius, right? And then we also have an angle here, theta. Theta can range from 0 to 2 pi, right? And then r can range from 0 to infinity. So we'd like to go ahead and make that change. Now we have two variables here instead of one variable, so we're going to have to do it's a little bit slightly more tricky. So changing this into the polar coordinates, you can do this a variety of different ways, and some of them are more interesting than others. And I've studied this already now, and seen some really good videos on YouTube about different ways that people will make this transformation, but I find it more simple this way. So we're going to convert y and then z into something that is that is compatible to the polar coordinates here. So if we take in this case, what I'm going to do is I take the sine of theta, right? The sine of theta. So this is going to be the opposite divided by r here, right? So the opposite here is y. So we have sine of theta is y divided by r, right? And rearrange that so y equals sine theta r. So that's our first conversion. And our second one here will be to convert z. So we need something that's related to z, and the cosine of theta is this adjacent line divided by r. So it'll be z divided by r. So we got cosine theta is z divided by r, and then we rearrange this to solve for z. So z equals r cosine theta. So we've done the first step here. So we've made this conversion already here. Now we've converted y and z into these values that are in the polar coordinate system. I think it's the end of this sheet, and I'll have to go to my second sheet after this. So if we substitute these in for z squared plus y squared, I get, and it has to end up equaling r squared. That's the only way this substitution makes sense, and it does. So we get r squared. So we have, let's see, the z squared would be r squared cosine theta squared, plus the y squared would be, well, for y, we have r sine theta, so it would be r squared sine theta squared, and we separate we pull out the r, right? So we have an r squared on both of these values here. So we'll just pull out the r. So we've got r squared times cosine theta squared plus sine theta squared, which we know equals 1. So r squared equals r squared. So we're really good. So then we can just go ahead and substitute r squared for z squared plus y squared after making this change here. Really cool, right? So now we've got one value to deal with, r squared. But we also need, just like if you recall earlier when we converted in the last video, when we made this conversion from x to z, we had to have the scaling factor. Where was it? Let's see, right here, right? It was this sigma, right? We had to get the scaling factor here. We're going to need a scaling factor here, but it's going to have to cover these two different variables, right? So we're dealing with two rather than one variable here. And to get that, we'll get something known as the Jacobian, and we'll take its absolute value, the absolute value of the Jacobian. So in this case, it's the scaling factor for us. So I'm going to pause the video, stop the video here, and then I'll do the last part in the next video.